the fact that you guys seem to be winding down, I want to talk about an approach here. For starters, you should have recognized that in order to answer the question, what is the normal force at point P, we had to use a conservation of energy approach. One of the cues was that the curvature of the hill made using dynamics and acceleration and kinematics to answer that question impossible. So the curvature is one cue that you're going to use conservation of energy. So when we go from point 1 to 2, we can think about this as, you know, if this is 0, we can move the kind of reference plane up here. And then if we do that, then we can ignore any gravitational potential energy at point 2, which makes our expression easier. And if we do that, then the height at point 1 is just 3 meters, or the difference between the starting point and the ending point, 5 and 2. It's interesting to note that if we ignored the rotational kinetic energy stored in the wheels, we would expect the system, in this case the cart, to be going 7.7 meters per second when it got to the top of the hill. That's if we ignored any energy that went into spinning the wheels. Because the wheels have non-negligible moments of inertia, we can see that some of the initial gravitational potential energy stored in the system at rest at the top, at point 1, goes into just spinning the wheels when it gets to point 2, which then lowers its translational kinetic energy at the top of the hill. So your approach should have been conservation of mechanical energy, recognizing that we have gravitational and the sum of translational kinetic and rotational kinetic when it gets to the top of hill 2. However, you had to make mental notes that this was the mass of the entire system. The wheels have mass and the block has mass. This is the translational kinetic energy, so it's still the total mass of the entire system. Eventually, we're going to recognize that I would be the moment of inertia of a solid cylinder, which you can derive through the inspection cylinder and the shell process. And we know that it's going to be 1/2 mr squared, and it's just the mass of the wheels. There are 4 of those wheels, so each one of them requires a certain amount of energy in order to spin it. The other big idea is the relationship between the tangential speed of the wheel and its angular speed. And we can say that the angular speed is the linear speed divided by the radius. And so therefore, when I square that, I get this expression that's ultimately going to get substituted here. You didn't have to do it that way, but I think that it's important to kind of algebraically do your work. As you saw last year on the Physics 1 exam, it's common to not be given numbers and to say, solve for the normal force at point 2 in terms of M and R and big R and all that kind of stuff. And so I think it does make sense. I actually started to plug numbers in, and then I stopped, erased my work, and went back and said, nope, you got to do this algebraically. The other piece that added a little bit of complexity here was recognizing that you weren't outright given the mass of each one of the wheels. You had to solve that using volumetric density. That is absolutely a down-the-middle, fair thing to ask in the course. You should be able to say, yeah, I know the density, and I know that density is equal to mass over volume. And so the first approach was to say, hey, I need to know the mass of the wheel. It's impossible to solve this question without that, or at least having some expression for it. We recognize that the density of steel times the volume of one of the wheels will be the mass of one of those wheels. I got about 0.77 or 3/4 of a kilogram roughly for each one of the wheels. If you wanted to find the contribution of the entire array of wheels, we would just multiply that number by 4, and now we can say, all right, well, that's 3.1, the mass of the block is 2, the mass of the system that we're talking about here is about 5.1 kilograms. And so step 1B is to find the moment of inertia of the wheel, asterisk, it would be fair in a multi-part FRQ to show the derivation of a cylinder, or show the derivation of a wheel, which is that shape, just a short cylinder. You could call it a disc. So we get 1/2 mr squared, where m is the mass of one of the wheels, r is its radius, and we get about 0.0025. Note the units. This is something that we rarely kind of discuss, units for moment of inertia, but it is mass unit times a distance unit squared. So you're going to get, in standard units, kilograms times square meters, not kilograms per square meter, kilogram times this square meters is the product. If you wanted to take a look at the moment of inertia of the array, we simply add them together because they're all resisting rotation. Step 1C is now, okay, we have our expression, gravitational potential energy, translational kinetic, rotational kinetic. Look at the system of substitutions that's done here. We get 1/2 little m, which is the mass of one of the wheels, times little r squared, which is the radius of one of the wheels, times 4. That's the moment of inertia of all 4 of the wheels, times v squared over r. Notice what happens, the r squares go away. I have an r squared in the numerator, r squared in the denominator. 4 in the numerator, 4 in the denominator. And everything just reduces to mv squared, where v is the translational or linear velocity of the system. I can factor it out, divide both sides by our binomial here, and solve for v, plug the numbers in. And what's nice is now that you get the number 6.7, and if you had recognized that in about 10 to 15 seconds, you could have calculated this without knowing if there was no rotational kinetic energy, if the wheels weren't spinning, if the block just slid down there, a 5.1 kilogram block slides down, this would have kind of strengthened your confidence in that answer. You should know that it's going slower because some of the energy went into the wheels, and this kind of validates that. This little check that we kind of looped around with, I think is not only satisfying, but I think is part of any good problem solver's kind of regimen or plan of attack. We have not answered the question. The question was, what is the normal force at point 2? Well, perhaps you started here when you drew a free body diagram and recognized that there was going to be a weight force going down and a normal force going up when it reaches the top of that curve, and that the weight force has to be larger than the normal force in order for it to be completing a vertical circle. There needs to be a leftover center-seeking force directed radially inward to the center of the circle here of radius capital R. And so now I can basically say, I can write a dynamics equation. I think it always makes sense to call radially inward positive. We know that's going to be the direction of acceleration, and so it just kind of reduces the number of negative signs we're going to have here. I'm going to get a weight minus the normal force is going to be equal to my leftover force. When I'm moving in a circle, we simply call leftover forces centripetal forces. I can now solve this for the normal force. It's going to be mg minus fc is equal to fn. Substituting in our standard, by the way, this might be more generally m times a sub c, where a sub c is a centripetal acceleration. That's a straight Newton's second law substitution for our leftover force, mn. But we're talking about a centripetal force being v squared over r. This is actually the only expression that's given to you on your yellow equation sheets, that centripetal forces are equal to linear speeds or tangential speeds squared divided by the radius. So that's where the mv squared over r comes in. This becomes mg minus mv squared over r is equal to the normal force. And so, you know, you could factor out an m. This is a mass of the entire system. It's 5.1 kilograms. G is 9.8. This is specifically capital R in this case. It's the radius of the larger circle here that the track is a portion of at the very top of the curve. And so at this point I can just plug my numbers in, and you can see then that V is requisite information, right? You can't answer what the normal force is without knowing how fast it's going at the top of the circle. So let's go ahead and just plug some numbers in. I'm going to get 5.1 kilograms, 9.8 meters per second squared. I'm going to subtract that from 5.1 kilograms times the 6.7 meters per second. I have to remember to square it because that was given to me that's what I solved for, but I have to remember to square it here. And I'm going to divide it by a very short radius here of 0.36 meters in the denominator. And so when I do this, that's my expression for the normal force. Let's see how the numbers work out. I get 5.1 times 9.8. So this is just the weight vector. It's 50 newtons, 49.99. So it's 50 newtons. Now let's see what the required centripetal force is in order for this to happen. 5.1 times 6.7 squared divided by 0.36. And I'm getting 636 newtons. So what is happening here if I need 636 newtons? The Earth is only providing 50 newtons of that. What happens to the cart? Is the normal force negative? Adam, what do you think?
It's just going to fly off.
It's going to fly off the track. Because it's going too fast and the radius of curvature here is too small, that implies then that you would need a negative normal force, a downward pulling normal force here in order to keep the cart on the track. If you guys have been to Six Flags, which of course we went to last year, you might recognize that on some coasters there are wheels underneath the rails. And those wheels underneath the rails provide negative normal forces, which is what makes it absolutely thrilling when your butt starts to come off of the seat because you feel like you're going to fly out of the cart. And that is, of course, what makes it thrilling. This is a bit excessive simply because of the numbers that I selected. And of course, if I had made the radius of curvature larger, then we would have had a different result. Are there questions on this?